Let's take a look at one of the most important applications of eigenvalues and eigenvectors for matrices, namely looking at when a matrix is what's called diagonalizable. We're going to start with an example. Let A be this 2 by 2 matrix, 11, negative 12, 9, negative 10. And we're going to start by just looking for eigenvalues and a basis for each eigenspace of A. So to remind you how that works, we're going to be looking at the equation determinant of A minus lambda I equals 0 and solving this for lambda. So we need the determinant of the matrix 11 minus lambda, negative 12, 9, negative 10 minus lambda. So that's going to equal 11 minus lambda times negative 10 minus lambda, and then minus 9 times negative 12. We work through simplifying this a bit. We'll get, I guess, 11, lambda squared, and then minus 11 lambda, and a plus 10 lambda, and a minus 110, and then this will be a plus, I guess, 108. Okay, and then this simplifies to lambda squared minus lambda minus 2, which we can factor to lambda minus 2 times lambda plus 1. So we set this equal to 0 and solve it for lambda. We find that our eigenvalues, I'm going to write these up here, our eigenvalues are going to be lambda equals 2 and lambda equals minus 1. And let's work through now a basis for each of those eigenspaces. So let's give ourselves some space here to work through those. So just a reminder, the eigenspace is going to be the null space of A minus lambda I for each of these lambda values we just found. And we know that these null spaces are going to consist of more than just the 0 vector by kind of the nature of how we found them. So let's first work on lambda equals 2. So we want to look at A minus 2I. That means we're looking for the null space of the matrix 11 minus 2, so 9, negative 12, and then 9, and then negative 10 minus 2 will be a negative 12. To find the null space, we'll augment this with the 0 vector, and we can row reduce this. You could go through each step, but we can maybe do a bit of this in our heads. We know that both of those rows are the same, so we can zero one of those out and then divide that row by 3. We'd get 3, negative 4, 0, 0, and then zeros here. We could, at this point, sort of scale this by another 3, divide by 3, but let's keep everything as whole numbers. And so our eigenspace corresponding to 2 is going to be the span of the vector. I guess this says, if our vector is xy, this says 3x minus 4y equals 0, which means that 3x equals 4y. So we could let, for example, x equal 4 and y equal 3, and we get a solution to that. So E2 is going to be the span of that vector. Let's look for E negative 1. So if lambda is equal to negative 1, again, we're looking for the null space of A minus lambda I. So that'll be 11 minus negative 1 will be 11 plus 1, which is 12, and then negative 12, and then 9, and then negative 10 plus 1 will be a negative 9. I'm going to augment that with the 0 vector again to find the null space. We could row reduce this to 1, negative 1, and then 0, and then 0, 0, 0. So E sub negative 1 will be the span of, I guess, just the vector 1, 1, working this out in a similar way that we did before. Okay, so we found the eigenvalues and the basis for each eigenspace of A. Now let's, kind of work our way through what it means to be diagonalizable and, kind of show that this matrix in particular is diagonalizable. The reason we can tell this, and we'll formalize this in a few minutes, but the reason we can tell this is because we can create a basis of R2 consisting of eigenvectors for this matrix. So we could take, for example, 4, 3, and I'll write this over here. So a basis of R2 could consist of just these two vectors, 4, 3, and 1, 1. We are guaranteed that these vectors are linearly independent. We saw that in a previous video that eigenvectors that correspond to different eigenvalues for a matrix are guaranteed to be linearly independent. And so we've got two linearly independent eigenvectors, or just vectors, two linearly independent vectors in R2. That means we've got a basis of R2. They are sort of guaranteed to span when we've got them linearly independent. Okay, so in the example, we found basis for each eigenspace consisting of these vectors. What we're going to do is form the matrix P, which has V1 as its first column and V2 as its second column. We could find the inverse of this matrix. Now we know this matrix is invertible, so P inverse is guaranteed to exist. P inverse exists since we know V1, V2 is a basis for R2, and therefore this matrix consisting of V1, V2 as the columns is invertible. So this is kind of the key. We need that, in order to create this invertible matrix P, where the columns consist of eigenvectors, we need enough linearly independent eigenvectors so that we can form a basis for, in this case, R2. Depending on the size of our original matrix, we would have to match the number of vectors to that size. So if we started with a 3 by 3 matrix, for example, then we would need 3 linearly independent eigenvectors, and so on. Okay, so we've got P inverse. I'm not going to go back and I'm not going to go through all the work finding P inverse. Given a matrix P, you can find its inverse. We did that in a previous chapter. And then we're going to let D be this diagonal matrix. So D is diagonal, meaning that the only non-zero elements in D are going to be on the main diagonal. And sort of specifically here, we're going to put the eigenvalues that correspond to the eigenvectors for that we formed our matrix P with. So if we go back here just a second, you see that E sub 2 is the span of 4, 3. So 4, 3 is an eigenvector corresponding to the eigenvalue 2. So D is going to have a 2 in the first position since P has the corresponding eigenvector in its first column. And then 1, 1 was an eigenvector corresponding to -1. So we're going to put the -1 in the second position of D, and to match with that. So you could have constructed P and D in a different way. You could switch the order of those eigenvalues in D, but you'd have to switch the order of those eigenvectors. You could also choose other eigenvectors to construct P with, right? So we know that any vector in the span of each of these two vectors, so any scalar multiple of them, could create another eigenvector. So there's sort of multiple ways to do this, but all right, we construct P, we've got D, and what's the sort of main idea? We can show that P, D, P inverse is going to be something special. Let's go through the computation of this. So first, let's maybe multiply P times D. So we would get, I guess, 8 plus 0, and then -1, and then 6, and then -1. And let's multiply that by P inverse. Okay, and so going through this carefully, let's see, we have an 8 plus a 3, so that's 11. We have a -8 minus 4, so that's -12. We have a 6 plus a 3, so that's a 9. And we have a -6 minus 4, so that's a -10. And hopefully this matrix looks familiar. this is the exact matrix we started with. This is our matrix A. In case you don't believe me, I'll go back a little bit so you can see. So A is 11, negative 12, 9, negative 10, which is exactly what we found as PDP inverse. So this sort of format where we can write A as this product, PDP inverse, where D is diagonal, is what we call diagonalizable. We say that A is diagonalizable. All right, so a few definitions now, now that we have that example under our belt. So to begin, we say that A is similar to B. These are going to be two matrices. If there is an invertible matrix P such that A equals PB P inverse. And this leads nicely into what it means to be diagonalizable. So a matrix A is diagonalizable if there is a diagonal matrix D and an invertible matrix P such that A equals PDP inverse. So that was exactly what happened over here, right? So A equals PDP inverse. So we'd say that A is diagonalizable. Okay. And the specific construction of PDP inverse are going to be important as well, not just the fact that, not just the fact that A is diagonalizable, but we'll see that construction in a second. Note here that a matrix is diagonalizable precisely when it is similar to a diagonal matrix. So this idea of being similar to a matrix is somewhat of a useful definition in its own right, but we'll usually, in this class at least for now, use it in the context of when a matrix is diagonalizable. Okay, and on to generalizing all this. So proposition 4.3.2, if A is an n by n matrix and there is a basis v1, v2 through vn of Rn consisting of eigenvectors of A having associated eigenvalues lambda 1, lambda 2 through lambda n, then we can write A equals PDP inverse, where D is this diagonal matrix where we put the eigenvalues down the diagonal and zeros everywhere else. And then P is the matrix that consists of, whose columns consist of the eigenvectors that correspond to each of those eigenvalues. You are welcome to change the order once you find all the eigenvalues, and you're kind of writing this diagonal matrix and this matrix P. You're welcome to change the order of things, but the column of the first column of P and that first entry of D need to be corresponding eigenvalue eigenvector pairs, and likewise for the rest. So make sure you do that. But then we've got this setup: A equals PDP inverse. We are going to explore why that is useful in a future video, but for now, let's just focus sort of on the fact that this can be done in this particular case. And let's look at a proof of this. So we're going to start with P equals V1, V2 through Vn, and D as lambda 1, lambda 2 through lambda n, where V sub I and lambda sub I are eigenvector, I should say, an eigenvector eigenvalue pair. Okay, and so just to remind you what that means that A V sub I, should use this notation, right? So A V sub I equals lambda I V sub I. That's kind of the key there. And so, so suppose we have this set up. We want to show that A equals PDP inverse. Let's consider A times P. So that's going to be just, by the nature of how we do matrix multiplication, A V1, A V2, down through A Vn. So the columns of AP are going to be A times the columns of P. That's just our definition of matrix multiplication. But A V1 is lambda 1 V1 because, V1, lambda 1 are an eigenvector eigenvalue pair. And A V2 is lambda 2 V2. Okay, and then down to A Vn, which is going to be lambda n Vn. But this is equal to P times D. If you take P and multiply it by D, again, kind of, thinking about how matrix multiplication works, we would end, and since D is diagonal and set up in this exact way, we would end up precisely with this equaling P times D. So we have that AP equals PD, but since P is invertible, because we have this, we know that the columns of P form maybe I'll write this. So since the columns of P form a basis for Rn, that implies that P is invertible, since those columns would have to be a linearly independent set. And again, if you go back to some previous chapters and previous videos, we looked into invertibility, and one of the equivalent conditions we could look at is when the columns are linearly independent, then our matrix is invertible. Okay, and so AP equals PD. So if P is invertible, we can multiply by P inverse on the right for both of these equations. So AP P inverse equals PD P inverse. Okay, but P times P inverse is just the identity. And so we have A times the identity. I ran out of space here. Let's go up here. So we have A times the identity equals PD P inverse, but A times the identity is just A. Okay, so you could see kind of where we used our different conditions here. We used the fact that the constructions of P and D, the eigenvector and eigenvalue pairs, to kind of get AV, this AP matrix, the AV1, AV2 through AVN, to the lambda1 V1, lambda2 V2 through lambda n Vn, which is going to be P times D. And we use the fact that the columns of P form a basis for Rn in order to, kind of show that P inverse exists. So we could write A equals PD P inverse. I will point out that, if we just wanted to get to this point, that AP equals PD, then we could do that with, without P being invertible. And that has some applications. We're not going to get into those here, but you may encounter those if you study a little bit more linear algebra, or go on to some more advanced classes where you look at things like Jordan forms and other kinds of applications. But for our purposes, we're only going to really worry about doing this kind of thing when A is diagonalizable, and we can really get to that sort of final form, that A equals PDP inverse. And again, we'll see why that is useful in a future video. But for now, we've defined what it means for a matrix to be diagonalizable and saw one example. In the next few videos, we're going to go through more examples. So we're going to look at matrices that are diagonalizable, some that are not, which will really kind of necessitate looking at matrices with repeated eigenvalues. And we're also going to a little bit explore this concept of complex eigenvalues and sort of what happens in those cases.